Welcome to Properties of a Tangent Line to a Circle. Our objectives are to investigate properties of a circle and a tangent line by constructing a tangent to a circle at a point on the circumference. Really quick, let's review. A tangent line is a line that intersects the circle at only one point. So be careful to understand the difference between a tangent line, which intersects at one point, versus a secant line, which intersects the circle. We'll draw one at 2 points. So in this case, this green line is a secant line, and it intersects the circle here, and then again here. And then compare that to a radius, which starts from the center and goes to the outside the circumference. Okay, let's go ahead and construct the tangent line to this circle O at point P. You are looking at the finished product, but we're going to start from the beginning. Our first step is to construct a tangent to the given circle at point P, a point on the circumference. So what we want to do is draw a line from the center at O through P, and we'll continue it beyond the circle. All right, step 2. With the compass on P, we're going to draw an arc on each side of P to create point Q and R. So what our goal is to put our compass here at P and mark off an equidistance area between P and our new point Q and P and our new point R. And now you can see that point Q and R are the same distance from P. Step 3 is with our compass on Q, we're going to set its width to a greater setting than QP. So in other words, we want it to be longer than halfway. Now we're going to make an arc in the location shown. Basically what we're going to do is either put an arc up here or we're going to put an arc down here. And in this case, we've made our arc up in this area. Now without changing the compass, we're going to repeat that same procedure for point R, and we're going to end up creating a point S up here. Notice what we have now. We have 2 points. We have point S and point P, and our final step will be to draw a line through point P and S. Now we're done. The line PS is tangent to the circle at point P. And if you didn't notice, that was the construction for a perpendicular bisector. By marking off equidistance from P, P becomes the midpoint. And so what we've done is we've created a bisector of this line QR, and it's perpendicular. So now we know that the relationship between the radius and this tangent line is that they're perpendicular. They form a right angle. Based on this theorem, or based on this construction, we now have a theorem that's called tangent to a circle theorem. And it says, if a line is tangent to a circle, then it is perpendicular to the radius drawn at the point of tangency. And we just proved that using a construction. We constructed a perpendicular bisector to our radius. And by that very construction, we know that it's perpendicular. Let's look at the converse of the tangent to a circle theorem. It states, if a perpendicular to the radius is drawn at the point of tangency, then the line is tangent to a circle. So this statement works both directions. Let's look at some examples. In our first example here, we have a circle. Notice that we have this radius x, and then we have a tangent line. And we know that this segment right here that has a 20 on it is in fact a tangent line due to the converse. of the tangent to a circle theorem. If a perpendicular to the radius is drawn, which in this case, this is definitely a perpendicular because of the 90-degree angle right here. If it's drawn at the point of tangency, then the line is tangent to a circle. So, we have a tangent line and a radius. We also can see that this forms a perfect right triangle. What we want to do is solve for x. So let's look at how to do that.
Here we're given a tangent segment and the radius of the circle drawn to that point of tangency, which we know forms a right angle. So now that we know we have a right triangle here, we can use the Pythagorean theorem to determine the value of x. So we'll use the Pythagorean theorem that states that the sum of the squares of the legs of a right triangle equal to the square of the hypotenuse of the right triangle. So this side is the hypotenuse, therefore it has to be C, and we'll let this side be side A, and this side be B. So we'll have x squared plus 20 squared must equal 24 squared. So now we'll go ahead and simplify this and then solve. So we'll have x squared plus 20 squared is 400 equals 24 squared is equal to 576. 24 times 24. So now we'll subtract 400 on both sides. That will be 0, so we'll have x squared equals, this will be 176. Now we'll square root both sides of the equation. Since x is a length, we're only going to have the principal square root, or the positive value. So we have x equals the square root of 176. Now we should try to simplify this. So let's go ahead and see if we can identify any perfect square factors of 176. This number is divisible by 4. 176 is 4 times 44. 4 is equal to 2 times 2, which are both prime. 44 is 4 times 11. 11's prime. And then 4 is again 2 times 2. So if we want to show some work here, we have x equals the square root of, we have 4 factors of 2 and a factor of 11. Every time we have 2 equal factors, we have a perfect square factor. So 2 times 2 is 4, that's a perfect square. 2 times 2 is 4, that's a perfect square. So this pair gives us a 2, this pair gives us a 2. So we have a 4 outside the square root, so 4 times the square root of 11. Now let's take a look at our second example. Again, it's the same type of problem. Here we're given a tangent segment and the radius of the circle drawn to the point of tangency. So we know we have a right angle here. So now that we have a right triangle, we can use the Pythagorean theorem to determine the value of x. But notice how now we're going to be solving for the hypotenuse. So this will be side C, and we'll call this side A and this side B. So again, the Pythagorean theorem, we have a squared plus b squared equals c squared. So now we're going to have 8 squared plus 15 squared equals x squared. Well, 8 squared is equal to 64. 15 squared is equal to 225. 64 plus 225 equals 289. Again, we're going to take the square root of both sides. And because it's a length on a triangle, we're only going to consider the principal or positive square root. So we have x equals the square root of 289. And actually 289 is a perfect square. It might not be easy to recognize, but 289 is equal to 17 times 17. So this simplifies nicely. X is equal to 17 units.
And those were 2 examples of how to find a missing side length. In the first case, you found just the radius, and in the second case, you found more than the radius. You found the radius plus this portion that extends outside of the circle. In other words, the hypotenuse of this right triangle. There's one more example that I want you to look at today. It's a little bit different. In this case, AC is tangent to circle O. So here's our tangent line, and here's circle O at point C. We want to find the length of AC. But notice we have BO, which is missing a measure. Can you think about what that measure might be? Let's watch the video and find out how to solve this problem.
Line AC is tangent to circle O at point C. So this is line AC tangent to circle O at point C. What is the length of segment AC? What is this distance right over here between point A and point C? And I encourage you now to pause this video and try this out on your own. So I'm assuming you've given a go at it. So the key thing to realize here, since AC is tangent to the circle at point C, that means it's going to be perpendicular to the radius between the center of the circle and point C. So this right over here is a right angle. And the reason why that is useful is now we know that triangle AOC is a right triangle. So we could use, if we know two of its sides, we could use the Pythagorean theorem to figure out the third. Now we clearly know OC. Now OA, we don't know the entire side. They only give us that AB is equal to 2. But the thing that might jump out in your mind is OB is a radius. OB is a radius. It's going to be the same length as any radius. So this is going to be 3 as well. It's the distance between the center of the circle and a point on the circle, just like the distance between O and C. So this is going to be 3 as well. And so now we are able to figure out that the hypotenuse of this triangle has length 5. And so we need to figure out what side the length of segment AC is. So let's just call that, I don't know, I will call that X. X. And so we know that X squared plus 3 squared, I'm just applying the Pythagorean theorem here, so plus 3 squared is going to be equal to the length of the hypotenuse squared. Is going to be equal to 5 squared. And I know this is the hypotenuse, it's the side opposite the 90-degree angle, it's the longest side of the right triangle. So x squared plus 9 is equal to 25. Subtract 9 from both sides, and you get x squared is equal to 16. And so it should jump out at you that x is going to be equal to 4. So x is equal to 4. X is the same thing as the length of segment AC. So the length of segment AC is 4.
And that was our last example for the day. But notice that in all of these situations, we are using Pythagorean theorem, and that you just need to make sure that you understand what the radius is. The radius is going to have the same measure anywhere in the circle, and so BO in this situation was also 3 because OC, a radius within the circle, was 3 as well. Hopefully, after this lesson, you understand the properties of a circle and a tangent line. You should also know the tangent to a circle theorem and its converse. If the line is tangent to a circle, it is perpendicular to the radius. And if we have a perpendicular to the radius, then it is definitely a tangent line. You should also be able to solve problems involving a tangent line and a circle.